The English Channel in early June, 1944, was a beast. Dark water churned under low clouds, pregnant with rain that hadn't yet fallen. In the hours before dawn, when the world was still caught between night and morning, thousands of vessels crawled across that grey expanse like insects across a steel plate. The sound was unforgettable, engines groaning, metal scraping metal, the constant slap of waves against hulls that rang with a peculiar, hollow resonance. If you had been there, standing on the deck of one of those landing craft, you might have noticed something odd. The walls around you, the floor beneath your boots, the very skeleton of the vessel carrying you toward the distant shadow of Normandy, it all felt different. Lighter. Thinner. Some soldiers whispered nervously about their tin boats, half joking, half terrified. They didn't know they were riding atop a revolution, that the material surrounding them represented years of obsession, ridicule, and stubborn genius. History books speak of D-Day in grand terms: strategy, sacrifice, the turning tide of a global war. But wars are won in the details. In the rivets and welds. In the choices made years before the first shot is fired. And on that morning, as nearly 160,000 men approached the fortified coastline Hitler called his Atlantic Wall, one detail mattered more than almost any other: would the vessels carrying them survive long enough to reach the sand? The question seemed simple. The answer was anything but. Because the metal those craft were made from, this strange, experimental alloy that glinted silver-white in the occasional break of dawn, shouldn't have worked at all. It was too soft, too unpredictable, too prone to failure under the exact conditions it would face on that beach. The British Admiralty had nearly abandoned it. Shipbuilders had cursed it. And the man who championed it? He'd been called a dreamer at best, a lunatic at worst. But as those aluminum hulls scraped across the shallows of Omaha and Utah, Juneau and Sword, a different story began to unfold. A story not of grand strategy, but of one engineer's refusal to accept the impossible. This is that story. His name has been largely forgotten, buried beneath the avalanche of more famous names that the war produced. But in the early 1930s, in the soot-stained industrial heart of Britain, there was an engineer whose colleagues considered him peculiar. Some used harsher words behind closed doors. He was obsessive, they said. Impractical. He spent his evenings in a cramped workshop that smelled of chemical fumes and burned metal, conducting experiments that seemed to lead nowhere. While other engineers focused on proven materials, steel, iron, the reliable substances that had built empires, this man was fascinated by aluminum. Not the industrial-grade aluminum already in limited use, but something new. Something that hadn't been done before. He filled notebooks with calculations, sketches of molecular structures, theories about how different metals might bond at the atomic level to create properties that existed in none of them individually. His supervisors were not impressed. Aluminum was expensive, difficult to work with, and worst of all, it was weak. You could dent it with your thumb. How could you possibly build something meant for combat from a material that crumpled so easily? When he proposed his alloy, a mixture of aluminum with small amounts of copper, magnesium, and other elements he refused to specify, the response was dismissive laughter. But he persisted. Night after night, he returned to his experiments. He tested different ratios, different temperatures, different manufacturing processes. His hands bore the scars of countless burns and cuts. His eyes developed the perpetual squint of someone who'd spent too many hours staring at molten metal. His wife worried. His friends stopped visiting. Yet he continued, driven by a vision that existed only in his mind: machines that could float and fly, that could carry men across impossible distances without the crushing weight of traditional materials dragging them down. By 1935, he had something. An alloy that was roughly 3 times lighter than steel but, under the right conditions, nearly as strong. It had other properties too: resistance to corrosion, the ability to be shaped into complex forms, a peculiar resilience under impact. He filed his patents quietly, with little fanfare. The industrial journals barely noticed. The military wasn't interested. He might have died obscure and disappointed, another brilliant mind whose timing was simply wrong. But history has a way of circling back to the ideas it initially rejects. And as Europe drifted toward war, as the impossible became necessary and the unthinkable became routine, someone remembered the crazy engineer and his impossible metal. The question was no longer whether his alloy could work. The question was whether it could work fast enough to matter. Understanding why aluminum seemed like such a poor choice for wartime vessels requires understanding the metal itself. Pure aluminum is soft, softer than many woods. It oxidizes rapidly, forming a white powder that can weaken structures. It has a relatively low melting point, making it vulnerable to fire. And perhaps most critically for naval applications, it reacts poorly with salt water, corroding in ways that steel does not. These weren't minor concerns. They were fundamental problems that suggested aluminum had no business being anywhere near a combat landing craft. Yet the engineer's alloy addressed each weakness through an elegant dance of chemistry that even he didn't fully understand at first. The copper added strength, not through bulk, but through the way its atoms dispersed throughout the aluminum matrix, creating barriers that prevented the metal from deforming under stress. The magnesium improved corrosion resistance by forming a protective layer that actually strengthened over time rather than degrading. Other trace elements, whose exact proportions he guarded obsessively, contributed properties that seemed almost contradictory: flexibility without weakness, lightness without fragility. When metallurgists finally examined his formula in detail, they found something remarkable. Under laboratory conditions, the alloy performed adequately but not spectacularly. But under stress, under the exact brutal conditions you'd find in combat, it behaved differently. It strengthened. The repeated impacts and temperature variations that would fatigue steel actually improved the alloy's performance through a process called work hardening. It was as if the metal became more resilient the more you tried to destroy it. There were still problems, though. Serious ones. The alloy cracked in extreme cold, making it unreliable in winter operations. It required specialized welding techniques that few shipbuilders knew. It was expensive, not as expensive as it had been, but still far costlier than steel. And most troubling of all, it was unpredictable. Two batches manufactured using identical processes could have subtly different properties, making quality control a nightmare. The British Admiralty's internal memos from 1942 and 1943 reveal the depth of their skepticism. One admiral called it a promising failure. Another suggested that aluminum might be suitable for aircraft but was manifestly unsuitable for seagoing vessels of any kind. The bureaucratic consensus was clear: interesting science, but impractical for war. What changed their minds wasn't new data or refined formulas. It was desperation. By late 1943, as planning for the invasion of France intensified, Allied commanders confronted a terrifying reality. They didn't have enough landing craft. Not nearly enough. Steel production was maxed out. Traditional shipyards were running 3 shifts and still couldn't keep pace. The invasion might be postponed or even cancelled, not for lack of will or troops, but for lack of boats. In that moment of crisis, the impossible metal started looking more possible. The logistics of Operation Overlord boggle the mind even today. Moving 160,000 men across the channel required not just a few dozen vessels but thousands, landing craft of various sizes, each designed for specific purposes. LSDs to carry tanks. LCIS for infantry. Smaller LCVPs, the famous Higgins boats, to make the final sprint to shore. The operation consumed resources on a scale never before attempted in human history. But by the autumn of 1943, the planners faced a problem that threatened the entire enterprise. Steel, the lifeblood of industrial warfare, was simply too scarce. Every ton allocated to landing craft was a ton taken from destroyers, tanks, or bombers. Churchill and Roosevelt exchanged increasingly anxious cables. Eisenhower, newly appointed as Supreme Commander, received reports that painted a stark picture: without a dramatic increase in landing craft production, D-Day would have to be pushed back, possibly into 1945. The Germans knew this. Intelligence suggested they were strengthening coastal defenses precisely because they believed the Allies lacked the capacity to launch an invasion in 1944. Every month of delay meant thousands more mines laid, more concrete poured, more artillery positioned. delay meant American and British soldiers would face an even more formidable Atlantic wall. In this context, a small experimental program that had been quietly testing aluminum landing craft suddenly became interesting to people who mattered. The tests had been conducted in Scottish lochs and along the wind-battered coast of northern England, far from public view. The results were mixed but not disastrous. The craft were lighter, significantly lighter, which meant they could be built faster, transported more easily, and would require less engine power. They could navigate shallow water more effectively. And critically, they could be produced using manufacturing capacity that wasn't competing with the desperate demand for steel. A decision was made, though not announced publicly. A portion of the landing craft for Overlord would be constructed using the experimental alloy. It was a calculated risk, the kind that only makes sense when all alternatives have been exhausted. If the aluminum craft failed catastrophically, if they crumbled under German fire or corroded overnight in salt water, the consequences could be devastating not just logistically but psychologically. Soldiers needed to trust their equipment. Doubt could be as deadly as any German machine gun. Orders went out to factories with instructions to begin production immediately. Specifications were loose by necessity, there hadn't been time for extensive testing. Engineers worked from blueprints that were updated weekly as new problems were discovered and solved. Welders learned new techniques on the fly. And always, in the background, there was the clock. June was approaching. The tides and moon phases that would make invasion possible came only once in a narrow window. There would be no second chance. The first full-scale trials were conducted in February 1944, in water so cold it burned exposed skin. The test crews, volunteers who knew they were riding experimental vessels, guided the aluminum craft through conditions designed to simulate the worst they might face. High seas. Heavy loads. Repeated beaching and launching. The goal wasn't to prove the craft were perfect, it was to discover how they would fail, so engineers could fix the problems before June. They failed in ways both expected and surprising. Welds cracked along stress points that hadn't shown up in computer calculations, which in that era meant tedious manual mathematics and small-scale models. Rivets popped under torsional forces. One craft developed alarming leaks after just 3 hours in salt water. But there were also unexpected successes. An aluminum LCI took a simulated shell hit, a controlled explosive charge, that should have torn open its hull. Instead, the metal deformed, absorbed the impact, and held. The same test on a steel vessel had produced catastrophic structural failure. Engineers descended on the test sites after each trial, taking measurements, cutting out sections of hull for microscopic analysis, interviewing the crews about every sound, every vibration. The notebooks filled with data, and gradually, a picture emerged. The alloy could work, but only if manufacturing tolerances were much tighter than initially planned. The welding had to be done at specific temperatures, with specific filler materials. The rivets needed to be placed in patterns that distributed stress more evenly. Changes were made daily, sometimes hourly. By April, production versions of the craft were rolling out of factories at increasing rates. Workers who'd spent careers building steel ships adjusted to the peculiarities of aluminum, the way it conducted heat differently, the way it sounded when struck, the strange lightness of components that should have been heavy. Some of the older craftsmen never made peace with it. They'd shake their heads, muttering about how war made you do things you'd never do in peacetime. Then came the trial that changed everything. A storm blew in off the North Atlantic in early May, unexpected and violent. 3 vessels were caught in it, 2 steel landing craft of conventional design and 1 aluminum prototype. The seas reached heights that no landing craft was designed to handle. When the storm passed, the 2 steel craft were found capsized, their hulls breached. The aluminum vessel, battered and listing but still afloat, limped back to port under its own power. The incident was never publicized, but word spread through the engineering teams and up through the command structure. Photographs show the damaged craft, hull plates dented, superstructure twisted, but intact. The metal that wasn't supposed to work had survived conditions that defeated the metal everyone trusted. Skepticism didn't vanish entirely, engineers are trained to distrust miracles, but it weakened. The aluminum armada, as some had started calling it, might actually make the difference. As May turned to June, as troops began their final preparations and ships gathered in the harbours of southern England, a quiet confidence took hold among those who knew what the landing craft were made of. They'd done everything possible. Now it was up to the metal, the men, and whatever fortune favoured the brave. The invasion began in darkness. Over 5,000 vessels moved through the Channel, the largest armada ever assembled. Among them, hundreds of landing craft constructed from the engineers' experimental alloy, their aluminum hulls painted with the same camouflage patterns as their steel counterparts, indistinguishable to the casual observer. But the soldiers cramped inside could feel the difference, the way the deck resonated differently under their boots, the peculiar lightness that made the craft respond more quickly to the waves. As dawn broke, as the first shells from German coastal batteries began finding range, the true test commenced. An armor-piercing round struck an aluminum-hulled LCVP 200 yards from Omaha Beach. The soldiers inside flinched, expecting catastrophe. Instead, the round punched through one side and out the other, leaving holes but not the catastrophic structural failure a similar hit might have caused in a riveted steel vessel. The craft kept moving. It reached the beach. The ramp dropped. This scene repeated hundreds of times across the invasion beaches. The aluminum craft absorbed punishment that should have sunk them. Shrapnel pitted their hulls but didn't penetrate. Near misses that would have warped steel frameworks left the lighter alloy dented but functional. There were failures, of course, craft destroyed by direct hits, by mines, by the 1,000 random chances of combat. But the rate of loss was lower than predicted. Significantly lower. In operations rooms back in England, engineers monitoring reports began to realize something extraordinary was happening. Radio communications mentioned boat still afloat despite damage, proceeding to beach after taking fire, hull integrity maintained. One officer, reviewing the damage reports that evening, noticed a pattern. The aluminum craft were more likely to be damaged but less likely to be destroyed. They could be hit, patched, and sent back into action. Steel vessels were either fine or sunk, there was less middle ground. The soldiers themselves had no time for such analysis. They waded through chest-deep water, struggled across sand studded with obstacles, fought their way off beaches where the surf ran red. Whether their landing craft had been aluminum or steel or would seem irrelevant in those moments of pure terror and adrenaline. But the fact that they'd reached the beach at all, that their vessel hadn't gone down in deep water miles from shore, made all the difference. There's a photograph, taken on D-Day +2, that captures something essential. It shows an aluminum landing craft, hull scarred by dozens of impacts, a small fire burning on the deck, limping back toward England with wounded aboard. The photographer caught it at an angle that makes the damage visible, huge dents, torn metal, a list that suggests it's taking on water. But it's still floating. Still moving. Still fulfilling its purpose. By the end of June, as the beachhead solidified and the invasion transitioned to the battle for Normandy, the aluminum craft had proved themselves beyond doubt. They'd carried men and machines across the deadliest threshold of the war. They'd absorbed fire from the most formidable defensive position Germany could construct. And they'd held. Not perfectly, war allows no perfection, but well enough. More than well enough. Reports filtered back to the factories, to the engineers, to the officers who'd made the decision to gamble on the experimental alloy. Numbers were compiled, percentages calculated, after-action assessments written. But perhaps the most eloquent testimony came from a sergeant who'd made 3 trips to the beaches in an aluminum craft. Asked by a journalist what he thought of his tin boat, he touched its dented hull with something approaching affection. "She brought me back," he said simply. 3 times she brought me back. What else mattered? War's end. The world turns. New crises emerge and old ones fade into history books and documentary films. The engineer who'd spent those obsessive years in his workshop, who'd endured ridicule and skepticism, who'd created the alloy that helped carry the greatest amphibious invasion in history, he didn't become famous. There were no parades, no medals, no public recognition of the kind that military heroes received. In part, this was deliberate. The aluminum alloy's composition remained classified for years after the war. The military advantages it conferred weren't something Allied governments wanted broadcast to potential adversaries. Patents filed under the engineer's name were sealed. Technical specifications were locked in archives with secret stamped across their covers. The men who'd benefited from his work didn't know his name, the public never learned it at all. He returned to civilian life in 1946, taking a quiet position at a manufacturing firm. His colleagues there had no idea of his wartime contributions. He was just another middle-aged engineer with receding hair and ink-stained fingers, no different from thousands of others. He retired in the late 1950s. He died in 1963, and his obituary ran only in the local paper, a brief mention of his career, his surviving family, the funeral arrangements. Nothing about D-Day. Nothing about the landing craft. Nothing about the metal that had changed everything. But the alloy lived on. Once the classification restrictions lifted, manufacturers discovered dozens of applications. The same properties that made it ideal for landing craft, lightweight, corrosion resistance, strength under stress, made it perfect for aircraft construction. For automobiles. For building frameworks and bridge components. The post-war aviation boom depended heavily on aluminum alloys whose development traced directly back to the formulas this forgotten engineer had pioneered. By the 1970s, aluminum was everywhere, so common it seemed unremarkable. The soda can in your hand, the airplane carrying you on vacation, the window frames in modern buildings, all benefited from metallurgical advances that had their roots in one man's wartime obsession. The irony is almost painful. He'd created something meant for war, for machines designed to carry men toward violence. But his greatest legacy was peace, the infrastructure of the modern world, lighter and more efficient because of what he'd discovered in those late-night experiments decades before. He never knew. Perhaps that's a mercy, or perhaps it's the deepest tragedy, to change the world and never see the change unfold. On the beaches of Normandy today, tourists walk where soldiers died. The bunkers remain, crumbling slowly under decades of wind and salt spray. The water is often calm, sometimes rough, never quite as dark as it was that June morning. And occasionally, at very low tide, pieces of wreckage emerge from the sand, rusted, corroded, barely recognizable fragments of the machines that made history. Some are steel, so degraded by time and salt that they crumble at a touch. But some are aluminum, and those pieces remain surprisingly intact. The alloy that was supposed to be too weak, too unreliable for combat, has outlasted the steel it competed against. There's a metaphor in that, though perhaps too obvious to need stating. Historians who study innovation have noticed a pattern. The breakthroughs that matter most often come not from committees or commissions, not from well-funded programs with clear objectives, but from obsession, from individuals who cannot let go of an idea even when every rational argument suggests they should. The engineer whose name we've lost exemplifies this pattern perfectly. Every rivet, every hull plate, every weld that held together on that June morning carried the mark of his refusal to accept the boundaries others drew around the possible. The soldiers who reached the beaches didn't know they were riding a revolution. Perhaps that's fitting. The most important changes are often invisible to those they save. The waves continue their ancient work, eroding metal and memory alike. But some things endure. Some ideas prove stronger than the skepticism that tried to bury them. And on quiet mornings, when the light hits the water just right, you can almost see them still, those hundreds of craft, glinting silver-white, carrying their precious cargo toward a distant shore.